Hello everyone, my name is Shunfeng. I work as a postdoctoral fellow in Quantum Photonics Lab in Hybridized University, UK. I'm supervised by Prof. Brian Geraldot. Today I'll talk about our recent progress on electrical field tuning of layer hybridized exciton in 2H, Bilayer and Trilayer MoSe2. First, I'd like to acknowledge my co-workers, my supervisor, my group mates, as well as our collaborators in Toulouse, France. So first, let's look at the transition metal tetracarbonate semiconductor. As we all know, the TMD monolayer they couple strongly with light, and the intralayer exciton where the electron and hole are within the same layer. They have very large oscillation strength. However, because of the lack of permanent static dipole, they have very low energy tunability. And in contrast, for the TMD heterostructures, they have internally exciton with electron and hole separated in two layers. And due to this strong permanent dipole, they have a quantum confined Stark effect with very high energy tunability. However, their absorption and their oscillator strength is pretty low, so they don't have much absorption, and you can only probe the internally exciton states in PL rather than absorption. And the community has been demanding a material system that has both strong oscillator strength as well as very good energy tunability to further integrate this TMD material into the optical cavities. So one way to achieve this goal is to look at the homo-bilayer TMDs with 2H stacking, for example, 2H-MoSe2 as shown here. So by coupling the interlayer exciton and the intralayer B exciton in this case through the spin-conserved hole tunneling, the hybridized exciton can marry property of both interlayer exciton and intralayer exciton. As a result, the hybridized interlayer exciton they possess very large Stark shift as well as good oscillator strength. To further push this field forward, it is necessary to look at other exciton-exciton coupling mechanism, as well as other type of TMD material toolbox. So here we study the MoSe2 system. Let's look at the exciton in monolayer MoSe2 first. Here for the intralayer exciton in monolayer, we have the ground state A1s as well as excited states A2s. And A2s is the Rydberg excited states of A1s. They are separated in energy because the inverse the n square law based on the hydrogen atom model as well as the different effective dielectric environment compared to the intralayer A1s exciton. And both X-A1s and X2 and A2s they have the same spin value configuration denoted as XA here. Then let's look at the exciton in bilayer MoSe2. Here we can see in addition to the intralayer A exciton in each layer, we have interlayer exciton with electron hole separated in two layers. And in 2H stacking, the layer 1 and layer 2 they are 180 degree rotated compared to each other. So the spin value configuration of K value in layer 1 are opposite to the spin value configuration in layer 2, so the spin index and layer index are locked in 2H bilayer. And here in the right figure, we have a 0-volt differential reflectivity measurement for the bilayer MoSe2. This denotes the absorption of the material. So here we have a strong XA1s, the interlayer excitons A2s, and the B exciton. And in this work, we focus on the evolution of interlayer exciton and A2s state as we turn on the electrical field. In the left part is our device structure. Our sample is encapsulated in boron nitride with a dual gate structure. So by turning the opposite sign for the top and bottom voltage, we can induce a pure electrical field to the sample without any carrier doping. With this configuration, we are able to probe our sample with various electrical field and magnetic fields at 4 Kelvin in a cross-stat. And in the right figure, as we can see, as we turn on the electrical field, we see a split and a linear shift of the interlayer exciton transition. And the effective dipole moment we get from the linear Stark shift is from 0.33 to 0.37. And moreover, as the interlayer exciton is shifting towards 2S state, we can see it changes the trend from linear shift to a relative constant energy. Meanwhile, for the A2S, it before the interlayer exciton was approaching, it has a relatively constant energy, and as interlayer exciton approached, they get closer in energy, the A2S state start to shift in a similar manner as interlayer exciton does. This features avoided crossing, which indicates the hybridization between interlayer exciton and the 2S state. So to further understand this phenomenon, we denote the interlayer exciton state-based hybridized exciton as XH1 and the 2S-based state as XH2. So we use a phenomenological model to model this phenomenon, considering the layer and spin index. And here we can see that we can well reproduce our experimental result, and the coupling strength we got is around 5 millielectron-volt. And moreover, we want to propose the mechanism behind this intralayer exciton coupling. So here in the left figure, as we can see, at 0 voltage, the intralayer 2S state and the interlayer exciton, they are largely decoupled, as we shown here using the Bilayer exciton state to denote them. And in the left figure, for example, as we turn the electric field along the dipole orientation, we are tuning the interlayer excitons close to the intralayer exciton in their energies. And then they start to couple to each other through the spin-conserved electron tunneling. As a result, the energy dispersion of hybridized state can be regarded as a voltage-dependent superposition of the Bilayer exciton energy dispersion. Moreover, as we can see, for this example, when the electron in layer 2 and the hole in layer 1, they only couple with intralayer exciton in the layer 1, and vice versa for the opposite dipole, they only couple to intralayer exciton in layer 2. So the interlayer exciton polarity and the layer index for A2S state are coupled. This means it's a layer selective coupling. Moreover, we perform magnetoreflectance spectra to study the effective G factor of the hybridized state XH2. Here we show electric field dependent semi-splitting of the hybridized state. As we know that the hybridized state can be regarded as superposition of Bilayer energy state, so is their effective G factor. So as we tune the voltage for the electric field, we can tune the effective G factor either close to the intrinsic intralayer A2S state or close to the intrinsic interlayer exciton state or something in between. And so we can tune the effective G factor continuously from around -4 to +10 through 0. And again, we use a phenomenological model to capture our experiment, and they reach good agreements. Last, we studied the actual field dependence of excitonic transition in trilayer sample. Here we can see in the contour plot of the derivative differential reflectance. First, we have two branches of intralayer exciton separated in energy. This is because intralayer exciton in top and bottom layer, they have different dielectric screening compared to the intralayer exciton in the middle layer. And then we have two branches of interlayer exciton, and one branch X1 has a massive stark shift, while the other branch has similar stark shift as in the bilayer sample. And also this big dipole, the X1, it features avoided crossing with the intralayer exciton. And it possesses overall 200 millielectron-volt stark shift. And the effective dipole moment we can derive from this X1 is around 0.72, which is beyond the interlayer distance. And this indicates that this big dipole X1, it comes from the transition from the top layer to the bottom layer across the entire trilayer sample. And meanwhile, for the X2, it has similar dipole moment as XH2 in the bilayer sample. So they have similar origin as a bilayer dipole, which happen between layer 1 and layer 2, or between layer 2 and layer 3. And they have different distinct stacking order for the X2 and the X1, which is AB stacking and A stacking, respectively. So overall, in this work, we promote a new type of TMD homostructure which possesses a large stark shift and enhanced absorption for the future light matter interaction applications. And also, we provide a new insight for exciton-exciton interaction, as well as a new way to engineer a big dipole in trilayer sample. That's it. Thank you for listening.